Today's lecture is on stresses in rigid pavement. So temperature stresses. So let us see the Westergaard's concept for temperature stresses. The temperature stresses are developed in cement concrete pavement due to the variations in the slab temperature. Now the variations in the temperature across the depth of the slab is caused by the daily variations, okay, whereas an overall increase or decrease in the slab temperature is caused by the seasonal variations in the temperature. Okay, so the daily variations in temperature causes the warping stresses in the reverse direction at the corner, edge and the interior regions of the slab. So during the day, the top of the pavement slab gets heated, okay, under the sunlight, when the bottom of the slab still remains colder. So the maximum difference in temperature between the top and the bottom of the pavement slab may occur at some period after the mid-noon. So this causes the slab to warp or bend, okay, as the warping is resisted by the self-weight of the slab. The warping stresses are developed late in the evening. Okay, the top of the slab gets heated up due to the heat transfer from the top, and as the atmospheric temperature falls, the top of the slab becomes colder, resulting in the warping of the slab in the opposite direction, and there is a reversal in the warping stresses, okay, at the different regions of the slab. So thus the daily variations in the temperature causes the warping stresses in the reverse directions at the corner, edge and the interior regions of the slab. So during the summer, as the mean temperature of the slab increases, the concrete pavement expands towards the expansion joints. So due to the frictional resistance at the interface, the compressive stress is developed at the bottom of the slab as it tends to expand. Then during the winter, the slab contracts, causing the tensile stress at the bottom due to the frictional resistance, again opposing the movement of the slab. Thus the frictional stresses are developed due to the seasonal variations in temperature. Now the frictional stresses will be zero at the free ends and at expansion joints, and increases up to a maximum value towards the interior, and thereafter it will remain constant. Now the temperature stresses of two types. Okay, first one is a warping stress and the second one is the frictional stress. So what is warping stress? So when the top and the bottom surface of a concrete pavement possesses different temperatures, the slab tends to warp down or upward, okay, including the warping stresses, inducing warping stresses. So the difference in the temperature between the top and the bottom of the slab depends mainly on the slab thickness and its climatic conditions of the region. So by the time the top temperature increases to T1 degrees, the bottom temperature may be only T2 degrees, and hence the difference between the top and the bottom of the slab will be T2 minus T1, that is T degrees. Okay, so you can see in this figure here, this is the warping of the cement concrete pavement slab. You can see here the wrapping of the cement concrete slab. This is taken from the reference Highway Engineering, KHANNA and JUSTO. So you can see in this figure here, the slab movement, okay, takes place in the vertical direction, which is due to the temperature differential between the top and the bottom of the pavement slab. So during the midday, the top of the pavement slab has higher temperature, okay, than the bottom of the slab. So this causes the top fibers of the slab to expand more than the bottom fibers, and the slab will curl, okay, the slab will curl at the edges. You can see here the slab will curl at the edges as shown in this figure, okay. So this phenomena is known as the warping down of the slab. So by the end, by about the midnight, what happens, the temperature of the bottom of the slab is higher than the temperature at the slab top. So the slab will wrap down during this time, as you can see in this figure. Okay, so the weight of the payment slab prevents the slab to take a wrapped shape, thereby developing stress in the slab, which are known as the warping stresses. So the magnitude of the warping stresses, they are maximum at the interior region and they are minimum at the corner region. Okay, the warping stresses are maximum at the interior region. So when the slab is wrapped down in the daytime, the warping stresses, the warping stresses are tensile in nature at the bottom of the slab. So in wrapped conditions, the tensile stresses are developed at the top of the pavement slab. Now, to minimize the temperature stresses in the pavement slab, expansion, contraction and the wrapping joints may be provided transversely across the full width of the pavement. Okay, so next we will see the warping stresses. So assuming a straight line variation in the temperature across the pavement depth, the temperature at the mid depth or the average temperature of the slab will be T1 plus T2 upon 2. So the stresses at the interior region in the longitudinal and transverse direction is given by Bradbury by this equation here. St T equals to E Et upon 2 Cx plus nu Cy 1 minus nu square, where St is the warping stress at the interior, E is the modulus of elasticity of the concrete, small e is the thermal coefficient, okay, of the concrete, then T is the temperature difference, okay, between the top and the bottom of the slab, then Cx is the coefficient based on the Lx, okay, Lx Ly in desired direction, then Cy is the coefficient based on Lx upon Ly in the right angle to the about direction. So nu is the Poisson's ratio. You can see here, this is given in the slide here. So the values of the warping stress coefficients Cx and Cy for the cement concrete pavement are taken from the chart. Okay, so we will get the values of Cx and Cy based on this Lx upon Ly and Ly upon L values. Okay, so Lx by upon L and Ly upon L, based on this we will get this Cx and Cy. Next, the warping stress at the edge region is given by this formula. St E equals to Cxe Et upon 2 and Cye Et upon 2, whichever is higher. Okay, so for corner regions, the warping stress is given by Stc equals to E Et upon 3 1 minus nu root of A upon L, where A is the radius of the contact and L is the radius of the relative stiffness. This is for corner regions. Okay, the warping stress due to corner regions we have to calculate using this formula. Let us see a problem here. So let us read this. Determine the warping stress at the interior, edge and the corner regions in a 25 centimeter thick concrete pavement with transverse joints at 11 meter interval and longitudinal joints at 3.6 meter intervals. So the modulus of the subgrade reaction K is 6.9 kg per centimeter cube. So assume temperature differential for day conditions to be 0.6 degrees Celsius per centimeter slab thickness. Okay, assume the radius of the loaded area as 15 centimeter for computing the wrapping stresses at the corner. So this additional data is given here. E equals to, that is thermal coefficient of concrete, 10 into 10 raised to minus 6 per degree Celsius. E, that is the modulus of elasticity of the concrete, 3 into 10 raised to 5 kg per centimeter square. Nu is the Poisson's ratio is 0.15. So what is given to us in this problem is 25 centimeter thick concrete pavement, okay, is given. So we have to determine the warping stresses. Okay, we have to calculate the warping stresses at the interior edge and the corner regions. Okay, so the modulus of subgrade reaction is given to us, K value is given. So we are given assume temperature differential for the day conditions to be 0.6 Celsius per centimeter slab thickness. So T will be, what will T be? T will be 0.6 into the slab thickness. It is 25 into 0.6, 0.6. Okay, so assume the radius of loaded area A is 15 centimeter. Okay, we are given this. So at this data is also given to us, Poisson's ratio E and E, small e. Okay, that is, what is small e here? Thermal coefficient of the concrete, and capital is the modulus of elasticity of the concrete. Okay, so let us see the solution. Okay, so first we need to calculate the radius of the relative stiffness. So calculate L. Okay, so L equals to E H cube upon 12K 1 minus nu square raised to 1 by 4. Okay, so substitute all these values here. Three into 10 raised to 5 into, this is given to us, okay, 25 cube upon 12, K value is given to us, okay, into 6.9 is K value. One minus 0.15 square. Okay, raised to 1 by 4. So this value comes out to be 87.2 centimeters. Okay, so we need to calculate Lx upon L. Next step, Lx upon L. Okay, what is Lx? Okay, 1 1 0 0. That is, we are given that in the concrete pavement, okay, 25 centimeter thick concrete pavement with transverse joint. Okay, you can see in this problem here what is given here. Determine the warping stress at the interior edge and the corner regions in the 25 centimeter thick concrete pavement with transverse joints at 11 meter interval. Okay, so Lx will be 11 meter and longitudinal joints at 3.6 meter interval. So Ly will be 3.6. So accordingly we have to calculate Lx upon Ly. So 1100, okay, upon, this is in centimeters, so convert it, 87.2. So this will be around 12.61. Okay, so from the figure we need to calculate what is Cx. Okay, from this figure, if Lx upon Ly is 12.61, okay, Lx upon Ly is 12.61, your Cx will be around 1.03. okay, from this figure. So 12.61 is a Lx upon Ly. So see, from this figure you'll get Cx, okay, around 1.03. Okay, so from the figure, from the graph, Cx value is 1.03. Okay, so next Ly upon L. Ly is in the 360. Okay, 360 upon 87.2. That will be 4.13. Okay, and similarly calculate from the graph. Okay, so we know Ly upon L is 4.13, so it will be around 0.55. okay, 4.13 is here around 0.55. okay, from this graph. Okay, so from graph, again from graph, we are getting Cy as 0.55. okay, so we are given, we have to calculate small t. Okay, what is told to us? Assume the temperature differential for the day conditions to be 0.6 degrees Celsius per centimeter slab thickness. So what is the slab thickness given to us here? 25 centimeter thick concrete pavement. So multiply. Okay, so T will be your small t. How will you calculate? T will be 25 into 0.6. okay, which is 15 degree Celsius. Okay, so next we need to calculate the interior warping stress. Okay, so interior warping stress okay, that is ST interior. Okay, so this will be, what is the formula for this? E T by 2. okay, Cx plus nu Cy upon 1 minus nu square. Okay, so calculate this. This will be equals to, this is given to us 3 into E value is given 3 into 10 raised to 5 into small e is also given 10 into 10 raised to minus 6. Okay, T we are getting it is 15 upon 2. Okay, so this will be 1.03. okay, plus 0.15 into 0.55. okay, upon 1 minus 0.15 square. Okay, so this will work out to be, after solving, 25.61 kg per centimeter square. So this is the interior warping stress. So next we have to find the longitudinal edge stress due to warping. Okay, so next is the longitudinal edge stress. Due to warping. Okay, so we have to find it out. Let us see how to find using Cx value as it is higher. Okay, so Cx we are getting it as how much we are getting? Let us see. Cx we are getting 1.03, Cy we are getting 0.15. So this is higher. Cx value is higher. Okay. Let us see. So find it out. Longitudinal edge stress. Okay. So ST E will be Cx E T upon 2. Okay. Let us continue next slide. So ST okay, what is Cx? We are 1.03 into E, we know it as 3 into 10 raised to 5, okay, into E is 10 into 10 raised to minus 6, okay, into small t is 15, okay, upon 2. So this value will work out to be 23.18 kg per centimeter square. Okay, so next is warping stress at the corner regions. Okay, so ST C, okay, will be E small e t upon 3 1 minus nu, okay, square root of A upon L. Okay, substitute all this in this equation. We know 3 E as 3 into 10 raised to 5, small e as 10 into 10 raised to minus 6, okay, t value is 15, okay, upon 3 1 minus nu is 0.15, okay, A value is given to us 15 upon 87.2. So this value will work out to be 6.36 kg per centimeter square. Okay, so this is warping stress at the corner regions. Okay. So next, coming to frictional stresses. So due to the uniform temperature rise and fall in the cement concrete slab, there is an overall expansion and contraction of the slab. Okay, since the slab is in contact with the soil subgrade or the subbase, the slab movements are restrained due to the friction between the bottom layer of the pavement and the soil layer. So this frictional resistance tends to prevent the movements, thereby inducing the frictional stress in the bottom fiber of the cement pavement. So stresses in the slab resulting due to this phenomena vary with the slab length. In short, the slab stress induced due to this negligible small whereas in long slabs which could undergo movements of more than 0.15 centimeter, higher amount of the frictional stress develops. Okay, so the equating the total force developed in the cross section of the concrete pavement due to the movement and the frictional resistance due to the subgrade restraint in the half the length of the slab. So SF into H into B into 100 equals to B into L upon 2 into H upon 100 into W into FA. SF is the unit stress developed in the cement concrete pavement. W is your unit weight of the concrete. Okay. F is coefficient of subgrade restraint. Okay. Value is taken maximum as 1.5. Okay. L is a slab length. L is your slab length and B is the slab width. Okay. Coming to the combination of the stresses. So it is necessary to consider the conditions under which the various stresses in the cement concrete pavements will combine to give the most critical combination. So during summer, what happens is the critical combinations at the interior and the edge regions during the midday occurs when the slab tends to wrap down. So during this period, the maximum tensile stress is developed at the bottom fiber due to wrapping. Okay, and this is the cumulative with the tensile stress due to the loading. Next, the frictional stress is compressive during expansion. So the load stress at the edge region is higher than the interior. So the critical combination of the stresses will be given as load stress plus the wrapping stress minus the frictional stress at the edge region. So during the winter, the critical combination of the stresses at the above region occurs at the bottom fiber when the slab contracts and the slab wraps down during the midday. So the frictional stresses and tensile during contraction. So the frictional stresses is tensile, okay, during the contraction. So the critical combination of the stresses will be given as load stress plus warping stress plus the frictional stress at the edge region. Next, at the corner region, the critical combination occurs at the top fiber of the slab when the slab wraps upwards during the midnights. So there is no frictional stress at the corner region. So the critical stress combination will be the load stress, okay, plus the warping stress. Okay, it's given as load stress plus the load stress plus warping stress at the corner regions. Next, coming to a problem, let us read this. So a cement concrete pavement slab of thickness 20 centimeters is constructed over a granular subbase having modulus of reaction 15 kg per centimeter square. So the maximum temperature difference between the top and the bottom of the slab during the summer day and night is found to be 18 degrees Celsius. Okay, the spacing between the transverse contraction joint is 4.5 meter and that between the longitudinal joint is 3.5 meter. The design wheel load is 5100 kg. The radius of the contact area is 15 centimeters. E value of the cement concrete is 3 into 10 raised to 5 kg per centimeter square. The Poisson's ratio is 0.15 and the coefficient of thermal expansion of the cement concrete is 10 into 10 raised to minus 6 per degree Celsius and the friction coefficient is 1.5. So using the edge and the corner load stress charts, okay, which is given by the IRC, and the chart for wrapping stress coefficient, we need to find the combination of the stresses at the edge. So first of all, what is given to us, let us see and what we need to find out. So a cement concrete pavement slab of thickness is given to us as 20 centimeters. Okay. Then modulus of reaction is given as, okay, what is given to us? First of all, we know the thickness. Okay. Thickness is 20 centimeters. Then what else we know? We know modulus of reaction as 15 kg per centimeter square. Then maximum temperature difference, okay, temperature difference between the top and the bottom of the slab during the summer day and night is 18 degree Celsius. Okay, so temperature. Then the spacing between the transverse contraction joint, so transverse contraction joint is 4.5 and longitudinal joint is 3.5. So design wheel load is given to us as 5.1, radius of the contact area, okay, as 15 centimeters. E value is given to us as 3 into 10 raised to 5 kg per centimeters. Poisson's ratio we know 0.15. Coefficient thermal expansion is given to us as 10 into 10 raised to minus 6. Okay, and frictional coefficient is given to us as 1.5. Okay, so what we have to find the combination of the stresses at the edge using the edge and the corner load stress charts. Let us see how to find this. This is the solution. So first of all, at the edge region, okay, first we need to find out at the edge region. Okay, so for h equals to 20 centimeter, okay, and k equals to 15 kg per centimeter cube. Okay, or the edge load stress from the chart. Okay, we need to find the edge load stress from the chart. Edge load stress, okay, from the chart. What is edge load stress given to us as SE, right? SC. Let us see what is the edge load stress. For H is 20. So this is the edge load stress chart. Okay, so what is given to us? H is 20 centimeter. So let us see, H is 20 centimeter here. This x-axis, H is 20 centimeter and K value is 15. So you can see this curves here. So K is 15. Here it lies, right? Here. So corresponding to H is 20. So SE will be here, around here, okay, corresponding to this and here, okay. So 24 kg per centimeter square, okay. So SC will be 24 kg per centimeter square. Okay, then we have first is A is the edge load stress from the chart, then warping stress at the edge. Let's calculate warping stress at the edge. Okay, warping stress at the edge. So first we need to calculate the radius of the relative stiffness. Okay, that is L. Okay, we know its formula. Let us calculate, substitute all the values. 3 into 10 raised to 5 into 20 cube, okay, upon 12 into 15, 1 minus 0.15, that is nu square, okay, raised to 1 upon 4. This works out to be as 60.8, okay, centimeters. Next, length of the slab Lx. So length of the slab Lx is given to us as 4.5. Okay, from the problem we know the spacing between the transverse contraction joint is 4.5. Okay, so length of the slab Lx will be 4.5 meters. So since it is in centimeters, we need to convert it. So 4.5 meters will be 450 centimeters. So wrapping stress coefficient Cx, we need to find it out. Okay, so warping stress coefficient but we need to calculate Lx upon L. So let us find Lx. What is Lx upon L? Okay, so Lx upon L, Lx is 450 upon L is 60.8. So this value will work out to be as 7.4. So what will be your Cx? Let us see. So Lx upon L is 7.4, okay, around here. So this will be 1.02. That is Cx will be 1.02. Am I right? So Lx upon L is, what is Lx upon L? 7.4. So around here 1.02. Okay. So this is from the graph. Okay, Cx value we are getting it from the graph. So it is equals to 1.02. This value is from the graph. Okay. Next, similarly find Ly by L. So Ly is 350. Okay. What is L? L is 60.8. So find this value will work out to be 5.75. Similarly from the graph you find it out. So what is Ly upon L? So Ly upon L is 5.75. So this will be around 0.87. Okay, around 0.87. So this equals to 0.87. This is also from the graph. Okay, so T is given to us as 18 degrees Celsius. Okay, so we need to find the maximum wrapping stress at the edge. Okay, maximum wrapping stress at edge. Okay, so this is given by this formula STE equals to E small t upon 2, okay, into Cx. So this equals to half into 3 into 10 raised to 5 into 10 into 10 raised to minus 6 into 18 into 1. Cx is 1.02. okay, 1.02. So this will work out to be 27.54 kg per centimeter square. Okay, so this is the maximum wrapping stress at the edge. Next we need to find the frictional stress. Okay, so C will be your frictional stress. Okay, so frictional stress is given by SF equals to W Lx small f upon 2 into 10 raised to 4. So W we know, okay, that is 2400 into Lx is 4.5 into small f is 1.5, okay, upon 2 into 10 raised to 4. So this value will work out to be 0.81 kg per centimeter square. Okay, so next is the combined stress at the edge region. Okay, D will be combined stress at edge region. Okay, so critical combination of the stress during the summer midday equals to load stress plus wrapping stress minus the frictional stress. So critical combination okay, critical combination of the stress okay during the summer midday will be load stress plus warping stress minus the frictional stress. Okay, so load stress is 24, okay, plus wrapping stress we got it as 27, okay, 27.54. Frictional stress we are getting it as 0.81 minus the frictional stress 0.81. So this will work out to be as 50.73 kg per centimeter square. So this is the combined stress at the edge region. So now we have to find for the corner region. So next is the corner region. Okay, so for corner region, so from the load stress we need to calculate load stress. So from the chart, H equals, so A for H equals to 20 and K equals to 15. So we need to find what is SC. Okay, so from the corner stress chart, okay, this is the corner stress chart. So for H is 20 and K is 15. Okay, K is 15. Your SC will be around 28. Okay, SC will be around 28 kg per centimeter square. SC is 28 kg per centimeter square. Okay, so this is for the load stress. Now for the maximum wrapping stress, that is B, let us see maximum warping stress. Okay, so that is ST E, which is ET upon 3 1 minus nu, okay, square root of A upon L. Okay, so substitute all this in this equation. E we know as 3 into 10 raised to 5, small e is 10 into 10 raised to minus 6, this is 18, okay, 3 1 minus 0.15, okay, a value is given 15 upon 60.8. so this will work out to be as 9.15 kg per centimeter square. So this is the maximum warping stress. Okay, next we need to calculate the frictional stress. This is 0 at the corner region. Okay, C is the frictional stress. Frictional stress 0 at the corner region. Okay, so D will be the combined stress at the corner region. Okay, combined stress of the corner region, that is the critical combination of the stress will be load stress plus the wrapping stress. Critical combination of stress, okay, in summer midnight will be equals to load stress plus the wrapping stress. Okay, so this will be load stress is 28 plus wrapping stress is 9.15. okay, so this value, this is equals to 37.15 kg per centimeter square. Okay, so it may be noted that the critical combination of the stresses at the edge region is higher than that at the corner under the identical condition of the pavement, okay, load and the temperature. So okay, with this I come to the end of this lecture.